And are we recording? There we go. Okay, so we are on the tail end of lecture 12 here. And let me share my screen here. Okay, actually, I'm just going to share the entire desktop. Okay, so we left off here doing inverse dynamics, and this is the process by which at the joint level we relate motion to the kinetic causes of motion. And that will, those specific causes within each joint will be two specific things. There'll be a net or resultant force at the joint and a net or resultant moment at the joint. So what specifically are we calculating with inverse dynamics? For the foot, for example, we're calculating the net resultant kinetics at the ankle. So that would be this force at the joint with both its horizontal and vertical component, and the torque at the joint with its rotational component there. Okay. So conceptually, remember the way that we do this is we take our body segments that include the joints that we want to know kinetically what's going on there. So if I wanted to know kinetically what's happening at the ankle and at the knee, I would take a or create a model of the foot and the shank. Why? Because those are the segments that contain the knee and the ankle. Okay. I then conceptually pull them apart at that joint, at that ankle there. And then on each one of those segments in isolation, I do a free body diagram. I draw all the unknown or all the known and unknown forces and torques acting on that body segment. Now, when I separate the shank from the ankle here, that introduces some internal forces, the forces and torques inside that joint, and that's this Fry, the resultant vertical force, and Frx, the resultant horizontal force, and then Tr here, the resultant torque. Okay. Most of the lecture for today will be about after we've made those calculations, how do we interpret them? But the way that I kind of like to conceptually think about what these are is like picture you have like a foot here. Okay. And then if we look at just say the vertical direction, if I apply a certain force that moves that thing vertically a certain amount, if I apply another vertical force that moves a little differently, another vertical force moves like that. So if I apply known forces to this thing in the vertical direction, it'll have a known motion from F equals ma, right? The deal here is I have this one unknown vertical force, the force inside my ankle there that's causing like my foot to not fly off my body in the vertical direction. And I don't know what its value is, but I know all the other forces here in the vertical direction. And I know from measurements like how this thing actually moved. Okay, so mechanically here, we are figuring out what does this one unknown force here have to be given these other known vertical forces and given how this thing actually moved. Okay? So that's essentially what we're doing with inverse dynamics in a vertical motion sense, a horizontal motion sense, and a rotational sense. Okay? So then I would do that whole analysis and I would figure out, okay, what are my net kinetics at my ankle here? I then follow my purple arrow here, moving one segment up my kinetic chain here, and I do the same analysis on the shank. I take my ankle kinetics and I flip them, multiply them all by -1 and stick them here on the other side, Newton's third law. And then I do my inverse dynamics here and figure out kinetically what's happening at the knee. Okay, then I have my net knee force and knee moments. Okay. Now, a thought exercise, then if I wanted to keep going, say I want to know what's happening at the hip, I do the same thing. I would take my next segment up in my kinetic chain, my thigh. I know the knee kinetics from already doing on the shank, and I could do inverse dynamics to figure out the net kinetics that are going on there at the hip joint. Okay. For like clinical gait analysis or for analyses of like athletes in sports that primarily involve like the lower limb, we typically stop there. We typically determine the net kinetics that are causing motion at the ankle and at the knee and the hip. For most clinical gain analyses, that's typically where things stop. So then what? After we have these resultant forces and moments at the joint, any particular joint, hip, knee, ankle, whatever, what do we do with these things? You can calculate the power at the joint. Remember, power is the rate at which work is done, work over time. Um, Work is force times distance, and distance over time is velocity. So mathematically, it also works out that you can calculate power as force times velocity. So if I take the resultant torque at a joint and multiply it by that joint's angular velocity, that gets me the power produced by that torque. And similarly, if I take that resultant force at the joint and multiply it by the joint's linear velocity, I get the power of that force at the joint. Okay. Where velocity and angular velocity there, those are the kinematics of the joint, how it's moving linearly and how fast it's rotating. All that is for just, again, kind of like we did with that long drawn out calculation of joint angles. No normal person would do this by hand. That would be just for one single frame of data, and then you do this for like every little frame of data that you're doing this analysis on. It's a very time consuming and laborious task. So there's automatic software that does these sort of things. Nobody actually does this by hand. If you determine the power of the joint as a function of time, remember, because power is the rate at which work is done, you can integrate that power over time and get the amount of work that the joint does. So moment at a joint, power at a joint, the work done by a joint, like why are all these things interesting? Like why is this important? Inverse dynamics for the last like, well, let's see, the first time somebody published anything on it was in like 1930, so that's coming up on like 100 years here. And somebody first did it in like a three-dimensional, like, clinical grade type gait analysis in like the 1950s or 60s or so. So it's a pretty venerable technique. It's probably the most popular and common analysis technique for doing like research grade biomechanics or for in clinical settings where gait analysis is done. Determining the torque and the work and the power at the joints is probably the most common thing that's done there for those kinds of assessments. So why? This seems like it's kind of important, but what do we do with these data? Why is it so important? Why is this of interest? So here, for example, is the data that you would get out of an analysis like this. This is, let's just look at the panel on the right here. That's the one for the knee in the sagittal plane. These are data for running, for the stance phase of running. On the top panel here on the right, the y-axis is showing the angular velocity of the knee in the sagittal plane as a function of the time in the stance phase, I think. The middle panel is showing the torque or the moment at the knee over that same time period, so that during the stance phase. And the bottom panel here is showing the power at the knee. Okay. Now let's just focus on the moment at the knee for a second. The sign on the moment here can tell you if you're willing to assume that muscles on both sides of the joints are not co-activated much at the same time, which in most movements we generally don't do a whole lot of that. If you're willing to make that assumption that I'm only using like my flexors at once or my extensors at once largely, then the sign on the moment here can tell you what muscle group is predominantly acting at that joint. And the bigger the size of the moment in that sign's direction is, generally the larger the force that group in muscles is producing. Okay. Now, if you're having trouble understanding why that is exactly, let's do a quick demo here. So here's my model of my knee, for example. And if I want to extend my knee, go from like a flexed position to an extension position, that's going to involve producing forces with my quadriceps that produce a force in this little tendon here. Okay, that tendon has a moment arm to the center of the joint here. And the bigger the force in that tendon, the bigger the torque you're going to get in the extension direction there. Okay. Similarly, if I want to flex this joint, go from an extended position to a flexed position, that's going to involve my hamstring muscles pulling on the back of my tibia there. Those hamstring muscles will have some moment arm to the center of my knee there. And so the bigger the force in my hamstrings, the bigger the torque I will get in the flexion direction from that joint. Okay? So it's not necessarily telling you like what is the actual force in the muscles, but generally speaking, I'll pull my picture back up here. Generally speaking, the bigger the torque here, the greater the amount of force the muscle group that's producing that torque is going to produce that torque. Now you can see here these are labeled, yes, with positive and negative numbers on the y-axis, but they're also labeled with anatomical terms, extension and flexion. So for this moment here, if we're on the upper side, like the positive side of zero here, that means the knee extensors are predominantly producing that moment. And if it was negative here, like these little blips of negativeness here, that's when the knee flexor muscles are predominantly producing that moment. So the sign on the moment can tell you which muscle group, flexors or extensors at the knee, is predominantly active there. And the bigger the magnitude of the moment is in that direction, the more force that muscle group would have to be producing to produce that moment, generally speaking. Now, the power here, power gets really interesting. Power, when it's positive, and where would this power come from? Well, it would be this moment here, the middle panel, times this velocity here, the upper panel. Product of those two things, force times velocity, gives you the power. When the power is positive, that means that whatever muscle group is active at that time from the moment is generating energy. And when the power is negative, it means that whatever muscle group is active at that time is absorbing energy. Okay. So it can tell us if a muscle group is generating or absorbing mechanical energy. Um, Energy in muscles is generated during concentric shortening contractions, and it's absorbed during eccentric lengthening contractions. So another way that you can think of the power here is it's telling us beyond which muscle group is active and how, whether it's producing relatively large force or relatively little force. It can also tell us how much or what type of contraction that muscle is doing. If it's a positive power, then whatever muscle group is active is acting concentrically. And if it's a negative power, then whatever muscle group is acting eccentrically. Okay. Now that makes sense if you think about velocity here. So to make that a little bit more clear, let me share a different screen. Where's my, there it is. Okay, you should be able to see here a program that has a skeleton with some red muscles on it. Can somebody give me a confirmation there?
Yes.
Okay, thank you. So this is a pretty cool program called OpenSim. It's a program, a free program that Stanford University makes. If you want to download it and play around with it, it's free. It's at opensim.stanford.edu. It's a popular program for biomechanics research. I use it for computer modeling and simulation, and you can make some nice little graphics and visualizations with it. So let's take a look at what happens to my model's muscles spanning its knee here when we change like the angle of the knee. Okay, so there's a lot of muscles there. I'm gonna clean it up a little bit and just show a few muscles. So let's hide all those. And then let's look at my right knee flexors. And then let's just show, what's a big one? Let's just show biceps femoris. And for my knee extensors, let's just show vastus intermedius. Okay. So there I've got a knee extensor muscle, one of the quadriceps, and a knee flexor muscle, one of the hamstrings. Okay? And then I can go over to my model controller here and I can change the flexion angle of the knee. So notice, let's get this hand out of the way if I can. How do I move the hand? Let's do some shoulder, right arm abduction. Let's try that. There we go. Okay. So as I flex the knee here in the model, pay attention to what's happening to the length of this quadriceps muscle and the length of this hamstring muscle. Okay. So here I'm going to go flex in the knee. And as I do that, you should see, as we flex more and more, that the quadriceps are getting longer and the hamstrings are getting shorter, right? I'm moving the insertion of the quadriceps further from their origin, and I'm moving the insertion of the hamstrings closer to their origin, right? And then opposite thing, if I extend the knee, right, then I'm um, making my quadriceps shorter and my hamstrings longer, right? And this kind of makes sense if we think about like stretching, right? If I want to stretch my quadriceps, I flex my knee. If I want to stretch my hamstrings, I extend my knee, right? So the kinematics of our joints can map anatomically to the kinematics of our muscles, okay? Now, let's extend this to the speed of motion. When I flex the knee here slowly, my quadriceps lengthen slowly, my hamstrings shorten slowly. When I flex the knee quickly, my quadriceps lengthen quickly and my hamstrings shorten quickly, right? So like directionally, the direction the joint is moving can tell you if the muscle is categorically like lengthening or shortening. And the speed at which the joint is moving in that direction also maps to the speed of the muscle, whether it's stretching slowly versus quickly, or whether it's shortening slowly versus quickly. Okay, so with that in mind, back to the data here. As my knee here, as it's got a negative flexion velocity, my knee is flexing. My quadriceps are getting longer, my hamstrings are getting shorter, right? So if my quadriceps are lengthening while the quadriceps are producing force, what happens to a muscle, or what mode of contraction is a muscle undergoing if it's producing force while it's actively lengthening? That's an eccentric contraction, and that's reflected here by a negative power. Okay. Now, look here beyond like about 40% or so of the gait cycle. That's where the knee velocity switches from flexing to extending. Okay, so now the knee is extending, it's moving in this direction, meaning the quadriceps are shortening, right? The knee moment is still positive, which we're calling an extension moment. So it's produced by the knee extensors, the quadriceps. So from 40% onward here, roughly, the quadriceps are producing force and they're shortening. Okay, and anatomically or physiologically, what do we call it when a muscle is shortening while it's actively producing force? That's a concentric contraction, and that's reflected by a positive power here. Okay. So moment here tells you which muscle group is active and kind of how active it is, how much force it's roughly producing. From the velocity, you can then figure out kinematically what's going on with that muscle while it's producing force. And then those two things combined together, the sign on the power can then tell you kind of the net result there in terms of what type of contraction that muscle is doing. If it's a positive power, that's a concentric contraction, negative power, eccentric contraction. If it's zero power, where the muscle's producing force and it's isometric, it's not changing length at all, that would be an isometric contraction. It's pretty rare in a movement like of, voluntary human motion where the joint's like literally not moving at all for any appreciable amount of time. But you can see here kind of towards the end of this period of time in the stance phase, the power is still a little negative, but only slightly negative. It's pretty close to zero. So we'd call that kind of like an essentially isometric contraction. So if the power ever is literally zero or close to zero, that's literally an isometric contraction or pretty close to an isometric contraction. Okay, so I gave you a lot of facts there on how we interpret these moments in relation to what muscles are doing. More important, rather than just memorizing those facts, is to understand why those assumptions are reasonable. Like, why is it okay here to look at the joint level and generalize that down to a smaller tissue level? And in which situations is it okay to do that? Can I always do that, like as a moment, always predominantly from muscle forces, or are there situations where it's not? And we haven't talked about those net forces at the joints. Everything we talked about there was just at that torque at the joint. So can we infer anything there from those net forces at the joints? It seems like there might be something interesting there as well. Now, to get at these interpretations of the joint level kinetics down to like the tissue level kinetics, let's think conceptually about like where these resultant forces and resultant moments at the joints came from. When we calculate them with inverse dynamics, we do so from the measured motion of the body and from the external forces on the body, namely the force of gravity and the forces due to environmental contact, like the ground reaction forces. And by that, I mean, if I go back to my picture here, like if I'm doing my analysis on my foot here, what I'm calculating are these unknown internal kinetics at the ankle, this net force at the ankle and this net torque at the ankle. And involved in calculating that is this gravitational force acting on the outside of the body, this ground reaction force acting on the outside of the body, and then the motion of that body segment. Okay, so I'm calculating these internal forces given motion and external forces. Okay, so that's where they come from, strictly speaking. Um, when we interpret them, though, remember that these net forces and net moments from inverse dynamics, these are not forces acting on the outside of the body. These are forces acting on the inside of the body, like within the joint, acting at the center of the joint, or in a net effect at the center of the joint. Now, this here is a famous picture in biomechanics. It demonstrates what's popularly called the indeterminacy problem. And it comes back to that point I was making in class a lecture or two ago, where if you have, say, three algebraic equations, a system of three equations, you can solve for three and only three unknown quantities. Okay? If you want to solve for eight things and you only have three equations, you're stuck. You can't solve for those eight things. If you want to solve for eight things, you would need eight independent equations there. Okay? What this picture is showing is the relationship between the resultant kinetics of inverse dynamics at a joint like the knee and the internal forces in all the specific structures that act at or around the knee or inside the knee. Okay? So what you're looking at here is this thick, dark black arrow. That's the net force from inverse dynamics. So if I back up a couple slides here, that big arrow labeled FK there and pointing kind of mostly downward like that, that would be this force right here. Okay, the vector sum of like the vertical component of the net force at the knee and the horizontal component of the net force of the knee. Okay. And then this other big thick line there with the double arrow labeled MK, picture like a torque going around that axis. And that's, again, if I back up a couple slides here, that's this net torque TR at the knee there. Okay. So those large thick lines labeled FK and MK, those are the resultant force and the resultant torque at the knee from an inverse dynamics analysis. Okay? Um, all these other little arrows here, the ones labeled FC, FL, FM, and then they have little subscripts because there's more than one of them. Those are the forces in all the little specific tissues and structures that carry forces at or around the knee. Okay, so the knee has something like 10 different muscles that span it, depending on what we call a muscle. And so you can see 10 different forces labeled FM here. F10 here, that's one of the gastroc muscle heads, and F4 is the other one. F5 here, you can see that big thick tendon there. That's the patellar tendon, the one that carries the load from all the quadriceps muscles. The knee also has some ligaments that span it and sustain forces. So that's FL1, FL2. At the time of here, we thought there was four knee ligaments. This is an older figure from an older paper. In the intervening time, we've discovered what we think is a fifth ligament at the knee joint, but several ligaments carrying forces here at the knee. And then you also have these two forces here labeled FC1 and FC2. Those are the two forces of articular contact at the knee. The femur here has these two condyles on it, medial and lateral condyle, that sit in the tibial plateau there, the top of the tibia, and they press, those cartilage surfaces press into each other in two different spots because of the shape of those condyles on the femur, and it generates these compressive contact forces between the top of the knee and the bottom of the knee there. Okay? So generally speaking, this diagram is showing one, things we've already seen, the net force from inverse dynamics at the knee and the net torque from inverse dynamics at the knee. But it's also showing all the forces and all the individual structures that span the knee here, all the forces and all the muscles and their tendons, all the forces in the ligaments, and all the articular contact forces, the forces due to surfaces of the joints squishing into each other like that. Now, just like we said, if I produce a force with my patellar tendon, that produces a torque about my knee. That's this little force right here. Okay? And that's not only true for the patellar tendon specifically, that's true for every tendon that spans the knee, every ligament that spans the knee, and all these contact forces there. Right? So this net moment at the knee from inverse dynamics, it's the sum of all the moments in produced by all these little forces that span the knee here. Okay? And similarly, this net force from inverse dynamics, it's kind of tempting to interpret that as like the compressive load in the joint, but it's not. What it is it's the sum of all the forces in all these little structures that span the joint. Okay, the sum of all the forces in the tendons, plus all the forces in the ligaments, plus all the forces in the cartilage. Okay? So that's how you kind of want to internally think about what we're calculating with inverse dynamics. It's this net force and this net torque, but structurally at the next smaller physical scale at the tissue level, it's the sum of all the moments produced by all the forces that span the knee. Doesn't matter if it's muscles, ligaments, cartilage, whatever. And it's the sum of, or the forces, it's the sum of all those individual forces that act at the knee. And here we're just showing muscle forces and ligament forces and articular contact forces, but there'd be other smaller forces in here, right? Like your joints are kind of held together by joint capsules, which is this kind of stretchy, elastic-like structure, and that produces a little bit of force. Your skin develops a little bit of tension in it, and that produces a little bit of force and torque at the knee. If you're wearing like a knee brace or like certain clothes that are tight fitting, those produce forces and torques at your joint. And that's what these inverse dynamics forces are. All those things are typically a lot smaller than muscle and ligament and contact forces, so we're not including everything here. But strictly speaking, this net force is indeed the net force. It's the sum of all the structural forces at the knee. And this net moment is indeed the net moment. It's the sum of the moments from all those little structural forces that act at the knee. So that's where you want to get started at in thinking about how do we interpret these inverse dynamics resultants at the tissue level in terms of what muscles or what other tissues might be doing. So that was a long-winded way of describing in English how we can interpret these inverse dynamics resultants at the tissue level. Down here, I have a much shorter description there shown in the language of math, right? So FR, this net force or resultant force that I calculate at the knee joint or at any joint in inverse dynamics. Internally, it's the sum of all the muscle forces at the knee, all the ligament forces at the knee, and all the contact forces at the knee. Okay? And then the torque at the knee, similarly, is the sum of all the forces in the muscles times all their little moment arms at the knee plus all the forces in the ligaments times all their little moment arms at the knee, plus all the forces in the cartilage, the articular contact at the joint, times all their moment arms to the center of the knee. Okay. Now, ideally, to say something interesting here, we would like to drop some of these terms, right? Like it would be pretty convenient if I could say, okay, this resultant force at the knee, is that like is that like the joint load? Like is that the squish between the cartilage surfaces? Like that'd be kind of useful if I could interpret that quantity like that, right? I could get the load on the joint without sticking like a invasive sensor between somebody's knee, which most people aren't going to want to do, right? Or this torque at the joint, can I interpret that in relation to what muscles specifically are doing? Is it okay to kind of ignore ligaments and ignore joint contact forces, right? I was already doing that in my previous example when I was talking about what does this torque at the joint mean. But why is that reasonable and when is that reasonable? When is it okay to attribute all of it or most of it to muscles and ignore ligaments and joint contact? Like, is this a good, reasonable, physiologically sound thing to be doing in general or in specific cases? So essentially what we're talking about here is in these equations that relate inverse dynamics forces to internal structural forces, we would like to be able to drop some of these terms. We would like to be able to say, oh, those forces are small, so we could ignore them. Or oh, these moment arms are short, so even if they get multiplied by a giant force, they're not producing much torque, so we're going to drop them. So let's see if we can do that. Not to say ligaments aren't important. Ligaments are very important. Your joints don't work very well without ligaments, and some of you may from sports or from other things perhaps had ligament injuries, and those can be pretty serious injuries. But generally speaking, for most normal motions in most normal ranges of motion, the forces in your ligaments are typically a lot smaller than the forces in your muscles or the forces in your cartilage. Okay. That's not always strictly speaking the case. There's certainly exceptions where that would be a bad assumption. Like if you're near like the very end range of motion of a joint. The reason I can't move my elbow into, beyond full extension there's a lot of reasons. There's a lot related to the structure of it. But one of the reasons is that when I'm in full extension there, that's when my ligaments start to get really stretched and tensed and start to really resist further motion there. And so that would be a situation where the ligament forces are perhaps large and I shouldn't neglect them, right? So if I'm studying like baseball fastball pitching or something where the elbow may indeed get vigorously into or beyond full extension, neglecting the ligament forces may not be a great idea. But for something like walking, where my joints aren't typically near the end range of motion a lot of the time, dropping the ligament forces from consideration here might be a reasonable idea. So by dropping them here, we're not saying ligament forces are literally zero. We're just saying they're close to zero because they're a lot smaller than muscle forces and joint contact forces. Okay. So that gets me started here. I'm now left with my net force at the joint being the sum of muscle forces and the sum of joint contact forces. If I can just drop one of these, then I can attribute that net force to some specific anatomical structure, so where now I'm getting somewhere. That would be an interesting inference, right? The problem here is that you can't drop either one of these because they're both simultaneously large and they both act in opposite directions. Okay. Remember from way back first day of class, we talked about that fella Giovanni Borelli, the father of biomechanics, and his lasting contribution to the field was this notion of the contractile theory of muscle actions, where when muscles produce force, that force is always directed in tension. It's always in a direction that's going to try to shorten the muscle and try to pull the joint together that muscle is surrounding. Okay? So when I have a joint here and I produce a force in a muscle that spans that joint, that muscle force is tensile. Okay, so let's give that a positive sign. That tensile force, kind of like if I pull on a rubber band, the rubber band is going to want to pull itself back together. Same thing here. I have a muscle, tensile force, spanning this joint. That tensile positive force is going to pull or those joint surfaces into each other and press them into each other, generating compressive negative forces in the contact within that joint. Okay? So generally speaking, if like I'm producing, say, 1,000 newtons of muscle force at the same time, that's probably resulting in roughly negative 1,000 newtons of internal contact between my cartilage surfaces, right? So I could get a net resultant force here of zero, and it doesn't necessarily mean my muscle forces are zero. It doesn't necessarily mean my contact forces are zero. Most of the time, it's going to mean that they're both really big by unknown amounts and just in opposite directions. Okay? So the long and short of it is that because these muscle and joint contact forces are both simultaneously large and act physiologically in opposite directions, one is tensile, one is compressive. The resultant joint force is then not as tempting as it might be. It's not like the load on the joint. It's not the compressive or the shearing load on the joint. It's just simply the sum of the muscle forces and the joint contact forces, right? So we can't really say anything particularly interesting about this net force at the joint. It gets used for some other things, like if you want to do more detailed analyses of like energy flow from sort of different parts of the body, or if you have special situations where like the muscles are not active, then any resultant force is due to joint contact. But generally speaking, for a movement like walking, even like impaired walking, it's not a very useful force for inferring like structural loading of the body. Okay, so what about our torque at the joint? We've knocked out this net force at the joint as being terribly useful at the structural level. Let's see if we can get somewhere further with the torque at the joint. Now, remember, my torque at my joint, it's the sum of the torques produced by muscle forces, so all the forces in all the tendons times all their little moment arms to the joint, plus all the forces in the ligaments times all their moment arms to the joint, plus all the forces in the cartilage times all their moment arms to the joint. Okay. Now, like we already said, we're going to drop ligaments from consideration here because those forces are typically fairly small compared to muscle and joint contact forces. Okay. They're fairly small. Even if you multiply them by a very long moment arm, they're still going to be a fairly small torque. Okay. That again leaves me with the same situation I had on the previous slide. I've got my net torque at the joint, and it's equal to the torque from muscles plus the torque from joint contact. Okay. Now, I was not able in the previous interpretation of the net force at the joint to drop my contributions from the cartilage from joint contact here, because remember those cartilage forces, those are large at the same time that muscle forces are large. Okay? I am able to drop them from the torque balance here, though, not because the joint contact forces are small, but because their moment arms are short. Okay, so that term drops out, and I'm left with the net torque at the joint being due primarily to the forces that the muscles produce multiplied by their moment arms to result in that torque. Okay, so the result or the consequence of this is that the resultant torque I determined from inverse dynamics, at least in the sagittal plane of the major joints of the body, can be assumed in most cases to be largely due to muscles. There's again particular cases where this wouldn't be a good assumption, but in general, in like the sagittal plane of the hip and the knee and the ankle, it's typically pretty safe to assume, okay, if you have a hip flexion torque, that's from your hip flexor muscles. If you have a hip extensor torque, the vast majority of that is from your hip extensor muscles. And then same thing for the knee and same thing for the ankle. Now, to understand this a little bit better, let's go back to my diagram here and say why exactly are we dropping these things? Okay. So notice here, my muscles, everything here labeled FM, FM6, FM7, FM8, FM3. These are all forces in tendons of the muscles. Okay. Look where those are in relation to the center of this joint. Okay. They're a fairly long ways away. They wrap around the outside of the joint, meaning in terms of at least in physiological distance, they have fairly long moment arms. Okay. So you're multiplying these fairly large forces by these fairly long distances to the center of the joint, getting fairly large torques. Okay? These ligament forces, like here's a ligament, let's find another ligament. There's another ligament. Ligaments also act kind of on the outside of the joint, but they tend to be a little bit closer to the center, but they tend to have fairly small forces. Okay, so forces being a lot smaller than muscles multiplied by moment arms that are a little bit shorter, probably not producing very large torques. Now, these joint contact forces, notice that those, remember we said because the muscle forces are large, those contact forces are going to be large, so we can't neglect them on the basis of the force being small. Those forces aren't small. But notice that those contact forces, they act in the center of the joint. They're real close to the center of the joint, not necessarily exactly in the center, but fairly close to the middle, much further or much closer to the center of the joint than the muscle forces which wrap around it. So even though those contact forces are large forces, because they're close to the center of the joint, they're getting multiplied by small moment arms and not producing much torque. It's similar to the doorway example where the handle is as far as possible from the hinge so that when I produce that large force on the door, it produces a large torque around the hinges. If I go here close to the hinges and push with the same force, I don't open the door as easily because it's not producing as much torque about that hinge. So handle clear out here, long way from the center, that's my muscle forces. Handle clear in here close, I can have a big force, but because it gets multiplied by a small moment arm, it doesn't produce much torque. That's my contact forces. So they're big forces at the joint, but because they're close to the center of the joint, they don't produce large torques at the joint. So that's the basis for dropping the contribution from ligaments to the joint torque and the contribution of articular contact forces, or the forces in cartilage, from the torque at the joint. And I'm left with this conclusion that at least in the sagittal plane of most large major joints of the body, the net torque at the joint is due primarily to the muscle forces acting on either side of that joint. So that all then flows down to the basis of the stuff that we talked about earlier on here, explaining the facts basically. So this is why when I look at then the power from that resultant joint force, that really doesn't get me anywhere in terms of saying something about the power due to muscles or the power due to cartilage or ligaments or anything like that. It's a useful quantity for examining like energy flow and certain definitions of like the efficiency of movement at like a limb level or a joint level. But at the tissue level, you can't really say anything interesting about it. The power from the resultant moment at the joint, though, because those can be attributed, at least in these particular circumstances in the sagittal plane, to the forces that muscles produce. We can then look at the sign on the power as telling me whether that active muscle group is acting concentrically or eccentrically. And then the sign on the moment can tell me which muscle group is active in that particular way. So what this sort of analysis looks like at the end of the day is something like this. On the left here is for walking, and on the right here is for running. The top row is the power from the muscles at the ankle in the sagittal plane. Middle row is for the knee, and bottom row is for the hip. Okay. The different lines here in each of these panels, like under walking or under running, they each have like four different lines, I think. Those are walking or running at faster and faster speeds. And all these, the solid black line, I think, was the faster speed, and the thick dash line was the slowest speed. And you can see things generally increasing as you walk or run faster and faster, which kind of makes sense. Going faster is more effortful, more difficult, takes more force, more energy, more work, more power, generally speaking. But from this sort of analysis, you can look at the timing in combination with like moments and velocities and stuff of which muscle groups are active and when, whether they're generating power versus absorbing power, what types of contractions those muscle groups are producing, how roughly speaking, how much force is in those muscle groups in like a relative sense, like, how much more force do I need to run at a fast speed versus a slow speed. And you can find like normative data for these type of things. Like if you take a bunch of healthy adults and just kind of average these over like a healthy normal gait and then applying it to an individual who's got an injury or a disability or an impairment, we can get an idea of where their shortcomings are, where their disability is exactly. Data like this is used quite a bit in clinical analysis of, for example, children with cerebral palsy. It's one of the main kind of places where biomechanics has like made a real world difference. It's very common in hospitals for like clinics that work with children with cerebral palsy to do like a gait analysis like we do in our biomechanics lab. And they'll use that information to plan for the surgeries that a child might undergo to like change the orientation of the limbs and change the attachment points and the wrapping of the muscles surgically to allow them to generate forces and torques and moments at these joints that are more similar to like a typically developing child. So an example of a place using these kinds of data where there's been like a real world clinical impact. Okay, that is all for today. I thought I saw let me stop my share here. I saw a message in the chat, I think. Jack asked, why would the hip actively be decreased similar in running gait cycles compared to the walking ones? Let me pull that back up here. So one thing to notice here is notice that like the y-axis here is on different scales, which is always kind of a no-no in science. And when you're making your graphs and you're comparing things side by side, make the y-axis on the same range. So it might look here like the powers are actually lower at the hip in running compared to walking, or it might look like in walking compared to running, like you need just as much power at the ankle to walk versus run, which most people would say no, that's probably not the case. It's deceptive because the scales here are different, right? The scale for running goes to 0 to 8 and for walking goes to like 0 to 5, for example. So if you put those on the same scale, you'd see the running be quite a bit more power, quite a bit more work, quite a bit more force than compared to walking, unless you're walking like a really fast speed versus running at a fairly slow speed. Uh, Fatima asked, can we go over the focus questions to ensure my understanding is correct? Normally, I don't give rote answers to those, but because I'm feeling generous today, I shall. Question. Oh, sorry, y'all can't see that. Let me turn my share on again. I'm out of practice with Zoom in the post-COVID era here. Okay, question one. This is kind of a general one. How do you do inverse dynamics? What data information are needed, and what are the steps involved? The way that you do it is by applying Newton's laws, laws of physics, at least the force laws of physics, F equals ma, and things like that, to a free body diagram of an individual body segment. The data that you need to do it are you have to have motion of that body segment, you have to have the external forces acting on that body segment, and you have to have the anthropometry of that body segment, its mass and shape and distribution of the mass. And so that was that business a lecture or two ago about figuring out from cadavers or MRI or whatever the inertial properties of the body segments. Steps involved are you gather your data, you develop your model of the body, you pull the body apart at the joints, and at each one in isolation, you do a free body diagram and apply Newton's laws to determine the unknown kinetics at that joint. You then move up the kinetic chain, apply Newton's third law to that joint, and repeat the process, successively going up the chain one segment at a time until you have all the kinetics at all the joints that you care about. Okay, that's the one question. This is kind of two lectures combined with one set of focus questions. So that's the one that would relate to lecture 11. The ones that would relate to lecture 12, that's the stuff we covered today on these second two bullet points on how do I structurally interpret the force from inverse dynamics and the moment from inverse dynamics. The force is easy. We don't interpret it structurally, but the more important thing there is why can't we interpret it structurally? It's because it's the sum of large muscle forces, which are in this direction, and large contact forces in the joint, which are in the other direction. So it's like if you add a big positive number to a big negative number, you get a small number, but it's not telling you anything about whether the first number is big or the second number is big. There's no way to figure that out from that particular joint kinetic quantity. So structurally or at the tissue level, we don't really say anything with confidence from the resultant force at the joint unless it's special contrived circumstances. The resultant torque at the joint or the resultant moment at the joint, because of the reasons we discussed towards the end of the lecture here, that at least in the sagittal plane in normal movements can be assumed most of the time to be due to the muscles acting at that joint, which gets us a kind of a joint level insight into tissue level in terms of what a really important, interesting tissue muscle is doing. Okay, I am going to stop the recording here, but I'm happy to stick around for a little bit if anybody has any questions.